Good morning. So, we have started to discuss neural networks, architectures, but they have many, nowadays billions of parameters, and we have not yet talked about how to find those parameters. And there's a lot to say about that. And this is the main topic of today and Thursday, how to find the parameters that allow the neural networks to perform the miracles that we see. Yeah? And so headline for today would be training neural networks. And formally, what we do is we look for parameters, up to billions of them, that minimize the sum of the losses incurred on our training set. Okay, so what do we have? We have a summation over our training samples, and we have a loss function that measures the discrepancy between the true label and our prediction. The prediction depends on some input and on the parameters, and then we can have regularizers on those parameters as well as on the function output itself. And this is now the standard framework of supervised learning. Yeah? This would be standard supervised learning. Okay, and now there's something to say about pretty much every single symbol I wrote on this board. Okay, so starting with the architecture itself, then we have a choice of various loss functions. We have a choice of what regularizers we're going to use. The design of the training set is really crucial. And then there is the optimization itself. And I think the only place I didn't put a footnote was on the labels themselves. These I consider as given. And we can now talk about each of these things in turn. So starting with the architecture itself. Architectural choices, there are many. Yeah, there is, of course, so first and foremost, the question, very broadly, what families of architecture do you use? The standard nowadays would be feed-forward neural networks, or maybe I should even say non-spiking, because in the brain, as you know, our neurons, they don't operate like the perceptrons that we had on the blackboard last time. But in our brain, you had this in biology, we have these action potentials, and there is much information coded also in the rate of the firing rate. These would be spiking neurons, and a scientific, so there is I would say, a niche of research devoted to developing that kind of neural network. And well, they have a lot going for them, because after all, the miracle of biology is that we run a pretty massive and impressive parallel processor on maybe 20 watt. And if you nowadays still, if you try and translate this into, if you would try to put this on GPUs, so first of all, we cannot quite do it yet. This real-time complex processing that we are able, or that we can accomplish. And on the other hand, if we were able to, this would be lots of kilowatts. Yeah. So nature has come up with a pretty impressive solution, and some people try and learn from that solution. Now, the skeptics, those who like to use non-spiking neural networks on GPUs, they say, well, when we built planes, we also didn't give them wings that flap as the birds do. We developed an alternative approach to flying. And well, this non-spiking neural networks is very much the mainstream nowadays. And by feed forward, what this means is that we have a directed acyclic graph describing the flow of information. So what that means is that we can have cycles. Right? This is a cycle, but if I do take the direction of these arrows into account, then I would say, so there, if you always follow the direction of the arrows, then there is no way you can return to a node once you have left it. And that would be a directed acyclic graph. And I here have drawn an irregular one from 2 inputs to a single output prediction. But most people who are interested in building the sparsest possible networks that accomplish a given task, they will look at such irregular structures. The mainstream architecture is much simpler. So here I'm discussing this question of when we have unstructured input. Yeah, we just have vectors, input vectors in this case, in this toy example, with 2 components. And the mainstream architecture would be to have the kind of perceptrons that we saw last time. I don't want to draw all the arrows here. And this would be called one layer. And the number of perceptrons in it would be the width of that layer. And then we would have another layer, which can have more or less nodes. Let's do more in this case. This would be another layer. And here the input from one layer only maps to the next layer immediately. Okay, this would be kind of standard architecture. And if people want to sketch this without drawing all the perceptrons, then what you could do is you could use just a vertical line for each of these layers. Okay, so if I wanted to summarize what I've drawn here, it would be 2 inputs and then a not so wide layer and then a wider layer and then a not so wide layer and then a single output. And if you want to abstract this even more, then you can just say, okay, I'm inflating the width and then I'm deflating the width. And so typical patterns you will see is, for example, from a number of input dimensions to go down to a low dimensionality and then to inflate again. This is used for purposes of compression and denoising and visualization. This here would be an example of an autoencoder. Okay, now here I was saying that usually nodes from one layer feed only into the next. In recent years, skip links have become really popular. And skip links, as the name implies, they skip over layers. So we could, for example, if we have a couple of layers of the same width, then what I've drawn so far was that each layer maps only to the next one. And what one can also say is that neurons from one layer are allowed to bypass their neighbor. Yeah? And then we can have a highway of skip links where typically summations are happening along this extra pathway. So if I drew the skip links in this kind of diagram, it would be to go from here directly to a layer further down. But here the width of these layers was differing. Yeah? Here I had 5 perceptrons, and there I had 4. And normally these skip links in present architectures are used here on layers that have same number of perceptrons, so that we can easily add up vectors of the same dimensionality. Okay, and if we use this kind of architecture, the way it is sometimes written is to say that we have here parameters associated with these different layers. These are now capital W's. I mean to show matrices here, because after all, this is a summary of many perceptrons, and each perceptron has a vector describing its inputs weights. And for many perceptrons, I can collect these in a matrix. And then I can say that I have some matrix acting on my input, and then I use some activation function, and so this is what comes out of the first layer, and then I act on it with another matrix of parameters, and this goes through another nonlinearity, and then you can iterate this kind of nested expression. Yeah? So if we have L layers, this is what it would look like. So without the skip links, that would be a very simple description of a multi-layer perceptron here. In this case, if the matrix is the same dimensions, that would be the same width in all layers. And then if we want to do classification, then at the end, well, we would have a softmax layer, and in the end, depending on how many classes we have, we would map to one hot vector with, if I have 3 classes, I would have 3, or if you want to take account normalization, 2 outputs, but normally 3. Okay, so these skip links. The folklore explanation of why they are good is to say that they help the gradient flow. So in particular, if we have this kind of nested structure, and I know my output is not quite right yet, and I'm going to use automated differentiation, as we will discuss on Thursday, to try and adjust the parameters. In the early phases, it is really difficult for the network to figure out, what it should do in the first few layers to create a representation that is nice for the later layers. And these kind of skip links help propagating information to the early layers and allowing them to try and do something useful early on in the training. Right, and then there is a different class of architectures that's popular with a subset of the community. So up there, we had here standard feed-forward neural networks that correspond to directed acyclic graphs. And then we can have recurrent neural networks. And so I might have two inputs, and I might have a couple of perceptrons here. And now these recurrent neural networks are most often used on time series data or on sequential data. And rather than just map output to a next layer, they can have recurrent relations. Yeah? So we can feed the output into itself, or we can take an output from a later layer and feed it into an earlier layer. So statisticians might call this autoregressive. These kind of links. And well, they make for very different properties. So here you can, for some input, ask what will be stable points, what will be fixed points, what will be attractors in this kind of system. And so the people studying this type of network, they are usually also interested in dynamical systems, in chaos theory, and so on. And our colleague Daniel Dostowitz here from Zentralinstitut in Mannheim, he's quite interested, for example, in this class of architectures. Okay, now this was like the macro view of what architectures can look like. But then there are so many small elements, yeah? So for example, we can look at the activation functions. And now I could draw you here a whole gallery of activation functions. A picture gallery. So the one we talked about when we were discussing logistic regression was, okay, it went from 0 to 1 smoothly. When we were discussing toy examples, we made this harder, and we looked at the step function. Other people used not this logistic sigmoid, but a hyperbolic tangent, so which gave you a range from -1 to 1. And actually, these three here were used very much in the early days of neural networks. And then came Geoffrey Hinton again, like in so many other cases. And with his student, he suggested the rectifying linear unit. Yeah? So it just cancels negative parts and leaves the positive parts unchanged. And this rectifying linear unit, it's difficult to overstate how important this was. That was really a game changer. They implemented it partly just because this was numerically cheap. Yeah, here I have to evaluate exponentials and stuff, or I need at least a lookup table. And here, well, you just look at the sign. And if it's positive, you leave as is. If it's negative, you set it to 0. And this sped up things, so you could do more training cycles per time. But it also really changed the training dynamics. We can look at that in a moment. Right, and then, well, you know, to complete this gallery, there are so many more things you could do. So, for example, I can now multiply this one and that one. And if I do, I get something which, well, looks approximately like so. So this was here the rectifying linear unit. I'm sorry, this is all small for people in the back. This would be a sigmoid logistic unit, I get, or sigmoid, yeah, linear unit. You can also use not the logistic sigmoid, but you can use the error function, which looks very, very similar. So the probit, you can multiply the ReLU with the error function. You get a function which is called GELU. And then we have leaky ReLUs, which do not stay zero, but they go a little bit, they become a little bit negative, and you have parametric and so on. Yeah, so the important, so there's the zoo. And the important thing is that it's nonlinear. So the one thing that's really important is that all of these functions are nonlinear, but other than that, there is great artistic freedom. Yeah? And nowadays, well, the trend is to have something like so. It has a few nice properties. It is differentiable everywhere. It is linear for large numbers. It does completely cancel the small numbers. But this bump to the left of the zero is found to be helpful. And then there is theory, some more hand waving, some more accurate arguing, you know, why this bump is good. Yes.
I think you told us the activation function is not linear.
Yeah. Yes, of course. The question was, why is it important that the activation function be nonlinear? I give two answers. The first answer was last week when we were discussing this projection to a higher dimensional space and how problems become linearly separable in a higher dimensional space. And now if I take two-dimensional input, and so I could take this two-dimensional input, x, and I could multiply it. So let's say here this has p equals 2 dimensions, and I could multiply this with a matrix q times p, where q is much larger than p. Now the nominal dimensionality of my data would be q. I get vectors with q entries, but the points would still lie on a two-dimensional plane in this very much higher dimensional space. And if I have a problem which is not linearly separable, you know, let's say I have one class here and I have the other class there. This is not linearly separable. So if I now map this to a higher dimensional space, but the points just stay on this two-dimensional hyperplane or plane, which is just embedded in a higher dimensional space, it still is not linearly separable. I have not gained anything. But by using the nonlinearity, I can make this kind of argument that we had last time. In particular, if I take here my points, if I take my n points and map them to an n-dimensional space, then I will always be able to find a hyperplane that separates any subset of points, no matter which subset. And the argument that I gave in more detail last time, okay? Or if we now look at this, if we now say the activation function is just the identity, then, well, this would just be a product of a couple of matrices. Yeah? So I would have a product of a couple of matrices in L layers, and I would multiply that with my input x. Well, and if I multiply several matrices, I get out another matrix. So this would just be a linear transformation as just described. There is one, it does become non-trivial here, because if I multiply all of these matrices that correspond to different layers, so even if I have no activation function or only a linear activation function, if I multiply all these matrices with each other, I will still get just a matrix, but here, if the lowest dimensionality was, for example, 2, then this matrix, even though it's a big matrix, will just have rank 2. Yeah, so if I have p-dimensional input, but I multiply it with this type of matrix, then this matrix has rank 2, and this is a non-trivial constraint on what I can express. But other than that, the nonlinear activation functions are crucial for the projection trick to kick in, or for my nested functions to be more than just a linear mapping. Okay. Good. Other questions? All right, so I've been raving about importance of activation functions. Let's look at this in pictures. Oh, it fell asleep, I think. Okay, sorry, this will be a moment. Well, and for a while, you know, this was the Wild West. So people were, so every self-respecting machiner wanted to have an activation function to his or her name. So many were proposed, you know, many more than you see in this gallery here. Many were reinvented. But nowadays, the ReLU, this is a solid choice. And well, people in my lab happen to currently like the ZeLU, but this changes every 2 years. Yeah, what is the current favorite? All right. Now, many of you know this webpage. Who has seen it before? Okay, it is a very nice one. It was made as advertisement, or probably written by some interns, but it was made as an advertisement for TensorFlow, a library for automated differentiation, which has since been superseded by PyTorch. So at the time, this was developed by Google, and it was very popular for a while. Okay, and I just want to show the impact of using different activation functions here. So we have two-dimensional input. We have this problem to solve, a classification problem, and we have this network where we use these inputs, just x1 and x2 as inputs, and then we have 3 neurons, and we have 1 output neuron. Yeah? So very, very simple multi-layer perceptron, and at initialization, it currently looks like so. Yeah? And now we can use the sigmoid, for example, and okay, let's just train this by gradient descent using technology that we will discuss on Thursday. And here is the loss on the training set and on the test set. And you know, it's not stalled, something is happening. But all right, look, here the loss went down a lot, and we find a very nice solution. It has just taken a while. Okay, so 800 epochs or so. And we can, and by the way, yeah, this is 1 neuron, the other neuron, the third neuron, and here they are combined. Blue means positive weight and red means negative weight. So they are combined appropriately to produce this output here, which really solves the problem nicely. Okay, let's try again. All right, and here it seems to get stuck in a solution which is not quite so pretty. It has not managed to really So, these are misclassified now, those red dots. It has not managed to close this circle nicely. Oh, okay, it has. All right, it grokked it. Good. And we can try again. Because I want to show that sometimes we do get stuck in a local optimum and we don't manage. Ah, good. Okay, not bad. All right. Okay, now if we think this is too slow, we could increase the learning rate. Now we have increased the learning rate, and normally I would expect this training to become less stable, but here somehow it doesn't move anymore. Let's make it larger still. Okay, prematurely here falls into some local optimum. All right, so I'm going back to the original learning rate, which was what? This, I believe. And now let's change to ReLU as the activation function. Bam. That was less than 100 epochs. We can try again. Ah. Not so great this time. Not going anywhere. Okay, it's not learning anything. This neuron here is dead. You see it has, we have had vanishing gradients here. These weights are 0, and it's not going to come back. Try again. Bam. Okay. So this was very fast. Try again. Again, we have a dead neuron. And this is nice, where we fluctuate and we are in some bad local optimum. And if I increase the learning rate, it doesn't get out of it to find anything meaningful. Okay, good. All right. So we have seen a few things, including that local minima, and so I just want to prevent this from going to sleep again. All right. And the importance or the impact of choosing this or that activation function. I highlighted this one here as being good, and it's defined as x times the logistic sigmoid. All right. Now, still on this theme of architecture, we're still here on footnote number 1 out of 5. An important thing is the numerics of how do we actually express f. So even once we have settled on an architecture, on an activation function, and so on, we need to decide how precisely we want to represent all numbers. And a frequent choice would be to use higher accuracy in training. So for example, use something which is called mixed precision, which modern libraries afford, where we can use floating point or FP for short, 16 or 32, where we use the higher accuracy for the most crucial bits of the neural network, like the derivatives with respect to weights. And at test time, which in this field is sometimes called inference, rather than just deploying at test time. At inference time, when errors matter less, you can quantize the neural network and use maybe FP16 or even only integer like int8, or in the most extreme case to just use binary weights. Now when you train a neural network and you then simply truncate all numbers, this is not going to give you great accuracy. So normally you train the network and then you fine tune it at this accuracy. And this is really useful for bringing neural networks on handheld devices and so on. It lowers the effort dramatically, of course. And here in Heidelberg, the lab of Holger Fröning is quite interested in this interplay of hardware and neural network. So how to simplify your neural network to make it run fast on this type of hardware. Okay. Good. So any questions about footnote 1 here for the architecture itself? Yes. So the question is, what's the impact of the data? And yes, I mean, first of all, the data matters a lot, and we will talk more about that. But secondly, you mentioned the example of, let's say, all numbers are large and all of our input is large and positive. Now, there are two things to say. One is we have all these perceptrons in our neural network, and we need to somehow initialize these weights. And they are normally initialized from a scaled normal distribution. Normal, and so in any way they are initialized such that we have both positive and negative weights. It can be normal, it can be uniform. The variance of this distribution is scaled to make sure that your input, if you take numbers which are too large, then you multiply large numbers with large numbers, and then you get numerical problems. So they are scaled appropriately, but these weights have positive and negative entries, and so at initialization, and so the network will be able to learn something even if my input is all positive. And then secondly, there's still this question of biases. So if we have x1 and x2, and I draw a single perceptron here in glorious detail, then we have this bias. So I have a multiplier here, W1, W2, and I have another multiplier there. And this was just this discussion that we had about homogeneous coordinates or not. So instead of having a separate bias here, I can introduce an artificial extra entry, which I call x0, and which is always 1. And if I do it like so, then I can write this entire thing here is just double transpose x, and I don't need to write plus b. And then this x is now implied to have this extra 1. And this is, so when I'm using this kind of notation, this implies that yes, we have biases also. And that means for large positive inputs, these perceptrons from the first layer, they can learn to subtract something. The question was, is it state of the art to center the data before putting it into the neural network? I wouldn't know. Peter, do you know? Is it recommended practice? So like batch norm layers, yes, batch norm I'll talk about later, yeah. So it's implicit in batch norm, and I'm not aware of having this extra standardization as best practice, but you know, maybe it helps, I don't know. Yeah. The question was, can we directly train with integer 8? So I think the practice is more to start with higher accuracy, and once you've managed to solve the problem, to then make it cheaper, as opposed to training directly in low precision. But I'm not familiar with this line of work. This is a half-educated guess now. Yeah. Yeah. Well, the thing is, so for applications like these handheld devices, usually, so let's say we want to have, you know, just a tiny neural network that recognizes if you're photographing food or sunset or something. Yeah. Usually there happens no more training on the mobile device itself. So people do it offline, and they have the big GPUs and so on. Yeah? And now the question is just one of path of least resistance. Is it easier to, if I know that in the end, for example, I want to deploy a neural network with binary weights, is it easier to directly try and train with binary weights? And that has all kinds of problems with non-differentiability and so on. Or is it easier to train a standard neural network first and then start quantizing? And what I seem to remember, and what would be my intuition, is that it would be easier to first use, you know, proper floating point numbers and then quantize afterwards. Quantize and fine tune afterwards. Okay. Any more?